These are the answers to homework 4B. First, the definitions you need to know. Now let's go to the questions. Number 1, write a balanced chemical equation for each of the following, each of which results in a reaction occurring. Indicate the phases of each reactant and product. 1A is the reaction of an electric current passed through molten sodium bromide. There's only one reactant in this reaction. That's NaBr, and it's molten. It's in a liquid state. If you pass a current through any ionic compound that's in a liquid state, the type of reaction that can occur is a decomposition, and the sodium bromide will decompose into elemental sodium and elemental bromine. So your two products should be Na and then elemental bromine, which is Br2. To balance the equation, a 2 would need to go in front of the NaBr. To balance the sodiums, a 2 in front of the Na. It said molten sodium bromide, so the phase is liquid. Sodium in its elemental state is solid. Bromine diatomically in its elemental state is a liquid. B, solid nickel 2 chlorate is heated. This is the second type of decomposition reaction we learned. Metallic chlorates, if you heat them, you can drive all the oxygen off of them. So nickel 2 chlorate has the formula NiClO3 taken twice. If you heat it up, the oxygen will be removed as diatomic oxygen O2, and you're left simply with the nickel and the chloride. Because the nickel's charge is positive 2, chloride's charge is negative 1, the product's formula would be NiCl2. To balance the equation, the nickels and the chlorines are balanced, but there are 6 oxygens on the left, so you need a 3 in front of the O2 on the right side to get 6 oxygens on the product side. So we heated up the solid nickel 2 chlorate. It produced nickel 2 chloride, which is an ionic compound, should have a high melting point, so we would predict it to be a solid. And then you produce oxygen, which in its elemental state is a gas. Second question, give the oxidation numbers of all the atoms in each of the following compounds. First is S8. This is elemental sulfur. Elemental sulfur is made up of sulfur atoms. They happen to bond together in octaatomic molecules, but they're still sulfur atoms. Atoms don't have a charge. Its oxidation number is 0. B, a tellurium -2 ion. Whatever the charge of an ion is, that is its oxidation number, so this ion would have an oxidation number of -2. C, the ionic compound lithium phosphide. When you have an ionic compound, the oxidation numbers just equal the ion charges, much like they did in question 2. But in this case, the ion charges will come from their positions on the periodic table. Lithium's in the first column on the periodic table, so its ion charges are +1, so its oxidation number is +1. Phosphide's charge from its column on the periodic table would be -3 for an ion of phosphorus, so its oxidation number will be -3. And then once again, notice when you're writing oxidation numbers, we don't add up -1 and -1 and -1 and put -3 here for the lithium. We write the oxidation number for one ion of the lithium, and people, when they look at this, will know, oh, just multiply the +1 by 3 to give you a total charge of +3 in the compound, and that is canceled out by the -3 for the phosphorus. The next ionic compound, metal and nonmetal, the oxidation numbers can be determined just from the charges of the ions. Cobalt, however, is a transition metal, so I can't determine its charge from its position on the periodic table, so I'll start with the chloride ion. Chloride ions are always -1, and because there's 3 of them in the compound, that means the cobalt's ion charge has to be +3, so its oxidation number is +3. E is sodium bromate. This is an ionic compound, so the sodium ion's charge can be determined from its position on the periodic table. It's +1. Then BiO3 is a polyatomic ion. Oh, I said sodium bromate. This is sodium bismuthate, sorry. So between bismuth and oxygen, oxygen has the higher electronegativity. The oxygen will be assigned an oxidation number of -2. So now here we go. You know, the whole compound must be 0. The oxygens, -2, -2, and -2 add up to -6. The sodium is +1, so you have to go, if you have a +1 and a -6, what does the bismuth have to be? So they all add up to 0, and that would be +5. This is an ionic compound as well, so we're going to do the same thing. We're going to get the oxidation number of magnesium from its ion charge from its column on the periodic table. So magnesium ions are +2, and so therefore the oxidation number of magnesium will be +2. This is a polyatomic ion. Oxygen is more electronegative, so the oxygen gets to be -2. And so now we have to work all this out to figure out the phosphorus. 7 negative 2s would add up to negative 14. 2 positive 2s would add up to positive 4. So we have a positive 4, we have a negative 14. That means the phosphorus have to account for positive 10. Plus 4 and plus 10 and negative 14 would add up to 0. If the phosphoruses must be plus 10 and there's 2 of them, that means each phosphorus must be positive 5. That's about as complex as you're ever going to see. So if you can figure that one out, then you're in good shape. In this one, ionic compound again, the calcium is positive 2. 2 ways to do the other elements now. If you just assume that this compound, by distributing the 2, has 2 nitrogens and 6 oxygens, the oxygen which is higher in electronegativity will be assigned a value of negative 2. So in this compound, there are 6 negative 2s. They add up to negative 12. And calcium is positive 2. So positive 2 and negative 12, the nitrogen must be positive 10. And therefore, if there's 2 nitrogens, each nitrogen must be positive 5. An alternate way you can do that is that because every nitrate ion is always the same, if you just take the nitrate out of the formula and write it down as NO3 minus and determine the O's are negative 2 each, and 3 of those would add up to negative 6, the nitrogen would have to be 5, so that positive 5 and the negative 6 from the oxygens add up to the overall charge of a nitrate ion, which is negative 1. I find that easier to do, so anytime you have a polyatomic ion in a compound and you know its charge, just pull it out and make the oxidation numbers of the elements add up to the charge of the polyatomic ion. Now, covalent compounds. Covalent compounds, we use electronegativities. The element with the higher electronegativity is oxygen, so that's going to be negative 2. And so if the oxygen's negative 2, the nitrogens have to suck it up and be positive. And in this case, each nitrogen would have to be positive 1, so that the oxidation numbers now all add up to 0. N2H4. Nitrogen has the higher electronegativity, so we're going to assign it a negative oxidation state, and hydrogen will have to be positive. We spoke before about how hydrogen is the nonmetal with the lowest electronegativity, so it's always going to be positive. Watch what happens here, because you can get a wrong answer. If you look at nitrogen's column on the periodic table, nitrogen ion should be negative 3. So if the nitrogens are negative 3 each, they add up to negative 6. The hydrogens would have to be 1.5 each, because 4 times 1.5 would be positive 6. And that's impossible. A hydrogen can't have an oxidation number of 1.5. So sometimes when you have a hydrogen in a compound, it's easier to start with the hydrogen and give hydrogen its oxidation number of positive 1, because it's the lesser electronegative element. So give the hydrogens plus 1 each, they add up to plus 4. The nitrogens must be negative 4, so therefore each nitrogen would be negative 2, and now you have the correct oxidation numbers for the compound. So moral of the story is, in covalent compounds, start with the O's and the H's, assign the O's negative 2, assign the H's positive 1, then work towards the other elements after that. Here's another covalently bonded compound. We'll do what we just said. We're going to give the hydrogens oxidation numbers of plus 1. We're going to give the oxygens oxidation numbers of negative 2. So the 2 positive 1 hydrogens would add up to positive 2. The 3 oxygens would add up to negative 6. So if these are plus 2 and these are negative 6, the silicon has to be positive 4. Next compound, polyatomic ion. The oxidation numbers will now add up to negative 1 instead of adding up to 0. And so the oxygens, being more electronegative than chlorine, will be assigned a value of negative 2 each. And if the oxygens are each negative 2, they add up to negative 4. So the only way these charges of these oxidation states can add up to the overall negative 1 is if the chlorine is positive 3, because plus 3 and negative 4 for the 2 O's would add up to negative 1. And then finally, the uranyl ion. Who wouldn't want to do the uranyl ion? So this one has oxygen as the more electronegative element. The oxygens are negative 2 each. Negative 2 and negative 2 add up to negative 4. So if the oxygens add up to negative 4, what does the uranium have to be to make the whole charge of the ion positive 2? And that would only work if the uranium is positive 6. So positive 6 and then the negative 4 from the 2 O's would add up to the overall charge of positive 2.